SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to the lecture 6, Carrier Transport Phenomena, where we will talk about the diffusions of the charge carriers. So this is a part of E207, Electronic Devices and Circuits, and my name is Deepak Jain. So in last lecture, lecture 5th, we talked about the drift current. So the current in semiconductors is primarily of two types. One is the drift, another is the diffusion. And we'll talk about that, what is the diffusion process and how it constitutes the current in the semiconductors. Then we'll talk about the parameters on which the diffusion currents depend. Just like in the drift current, we introduced the concept of mobility, we understood the mobility, the ease with which these charge carriers can move in the semiconductors and in case of a drift current. So similarly, a diffusion coefficient is something which decides the easiness, like how these charge carriers can move in the semiconductor. So this basically forms the diffusion current. So we'll talk about the total current in the semiconductor, diffusion and drift. Then we'll talk about how this, when both currents are there, how the formation of electric field happens in case of an equilibrium, and why it is so important because we are going to deal with lots of electronic devices where we will have the concentration gradient, and diffusion current is very, very important. And we need to keep in mind that this diffusion current is not a part of conductors. So this makes semiconductors fairly unique. And then last we'll talk about Poisson's equations. That is also very, very important to calculate the electric field in semiconductors when charge distribution profile is given. Okay, so let's start the lecture. We'll start with diffusion. So I'm sure like you must have noticed the aroma of the outstanding food when you are passing by through a restaurant, and you must have noticed the scent of the perfume when you are passing by someone wearing that perfume. So you might be interested to know that what is the reason behind that, like how this smell propagate. So basically it's like from one molecules moves from one place to another because of the concentration gradient. So this is a basic concept of diffusion, and it do happen in semiconductors. So when there are excess charge carriers are created non-uniformly in some part of a semiconductor, then the electron and hole concentration, both, like it applies of course to both, will vary with position in the sample. Okay, so for an example, at some place you introduce a large amount of these electrons or holes, so slowly they will start diffusing in other part of the sample. So under the condition of equilibrium, of course they will all be equal, but there will be a concentration gradient initially and the current will form because of the motion of these electrons and holes. So such spatial variation or gradient basically either in N or P, and which results in the net motion of the charge carriers, and this type of motion is known as the diffusion, and this is a very important transport process in semiconductors. So you can say that the diffusion is a natural result of the random motion of these individual molecules. Okay, so let me draw some diagrams to explain it in a better way. For an example, let's say there is a region full of these electrons or holes or whatever you want to say. And let me draw the concentration profile with respect to X. So it will be something like that. So in region 1, it's full of electrons, and in region 2, there is no electron. Maybe like by some process, some uniform illumination in this region, a large number of electrons has been produced. So now what will happen, that slowly these electrons will start moving from region 1 to region 2 because of the concentration gradient. So in that case, if I draw again this diagram, how it will look like? It will look like something like that. Region 1, region 2. So some of these charge carriers will move here. Something like that. So slowly it will diffuse, and after some time there will be a stage when it will be in equilibrium. So all of these are in the same states. After a sufficient time. And if I draw the profile, it will look like something like that. Concentration Cx with respect to x, or something like this. And at some time, at this stage, it will look like something average concentration. So you can say diffusion is a process because of the gradient, concentration gradient, and the molecules from a high concentration region move to the low concentration region because of the thermal motion. Okay, so I can draw one more diagram to explain it in a more better way. For an example, let's say initially the concentration profile is something like this, Nx at time t equal to 0, and this is x, sorry. Now what will happen at time t greater than 0, which is, let's say, t1. So this profile will become something like this, and at time t2, which is greater than t1, this will become something like this. So it will settle down. So you can see the spreading of this pulse initially because of the diffusion. So this basically happens because of the rapid thermal motion. Also, the other important things which plays the role is the scattering, as in the case of this drift current, scattering due to lattice atoms, due to impurity, and many other things. So there is some connection between the diffusion and the drift, though the cause is different. In drift, it's the electric field which led these charge carriers to drift, and in the diffusion case, it's a concentration gradient which led this diffusion current or the propagation or the movement of these charge carriers. But there is some relation. What restricts them, like what limits their motion? Again, the scattering is involved. So there has to be some relation, and we'll talk about that in a later part of this lecture. So I hope you could understand a little bit about diffusion. So let's develop some mathematics of the diffusion. So for an example, like what will be the relation? Okay, ultimately our goal is to calculate the diffusion current, and in order to calculate the diffusion current, first we need to calculate the flux. Okay, flux of these charge carriers. So let's say this is our profile, and for easiness, let's see the concentration gradient in one direction. Let's not talk about all three directions, only one direction. Okay, so this is Nx and this is x again, and assuming the same distribution, something like that. So to develop some mathematics, we can okay, so this is the profile Nx versus x. Now we can divide this into small parts, let's say L bar on the x-axis. So this L bar is mean free path. So as the name indicates, this is the distance between two scattering events. If you remember, we talked about mean free time in the last lecture, which is represented by T bar. Okay. So, the time difference between two collisions. So, L bar is the distance travelled between these two scattering events. So, if we distribute this x-axis in terms of L bar, so let us say we get this L bar, then the second L bar. Of course, this L bar is fairly small. So, something like that, we can divide the whole region into these small L bar regions. And let us pick any of these two adjacent ones. Okay. So, what will happen, and let us call this first region to be region 1 and the second to be region 2. And let us say N1 is the density of charge carriers in region 1 and N2 is in the region 2. So, there is a gradient N1 and N2. So, charge carriers will move from N1 to N2 region, right, because of the concentration gradient. But we need to keep in mind that there is an equal probability of this movement from one side to another side, like they can move from either this side to this side, and also there is a probability from N to 1, from region 2 to 1. So, if I want to calculate the net movement of these charge carriers from region 1 to 2, then I have to assume, let us say, the number of charge carriers moving from region 1 to 2 first. Okay. Let us say 1 to 2 which are moving, and similarly N to 1 which are moving from region 2 to 1, and then I need to subtract them. So, net number of electrons, let us say we talk about electrons, of course, it is applicable to holes as well. Number of electrons moving from region 2 to 1 should be equal to half N1 LA minus L bar, half N2 L bar A. A is the cross sectional area of this region or whatever semiconductor or material we are using here, and L bar is this distance. So, L bar into A gives the volume, and N1 we know this is the concentration per centimeter cube or per meter cube, like per volume you can say. And why this half is being used here? That is a good question. As I said, the probability of moving in this direction and in this direction is equal. That is why half is being used. So, this is the net flow from region 1 to 2, and this is the reason, this is the net flow from 2 to 1. So, overall from N to from region 1 to 2 would be equal to this, which comes out to be half L bar A N1 minus N2. Okay. Since concentration gradient is there, N1 and N2 are involved, if they would have been equal, it would have been equal to 0. So, net number of electrons moving from region, sorry, it is from 1 to 2, I made a mistake here, from 1 to 2 are half N1 L bar A minus half N2 L bar A, which becomes half L bar A N1 minus N2. So, this is the net flow, and obviously we can see because there is a difference between N1 and N2, that is why it exists. Now, we will talk more about that. So, let us derive some relation based on that. So, this is basically can be seen as a flask. Okay. If we just calculated the net flow of the charge carriers, if we do it per centimeter square, we just need to derive this, divide this expression by A. Okay. So, it becomes half L bar N1 minus N2 and divided by time in order to calculate the flask. So, flask is basically your charge carrier movement per unit time per unit area. So, this gives you basically the flask of these charge carriers moving from 1 to 2 per unit centimeter square per unit time. And this is more or less known as the Fick's law. I hope you must have heard about that. Okay, so now our interest is in to calculate the diffusion current. So we are going into that direction, but before we go into that direction, so we can represent this N1 minus N2 in terms of some derivative, right? So we can write N1 minus N2 concentration difference from region 1 to 2 can be equal to Nx minus Nx plus dx divided by dx, and this whole term can be multiplied by L bar. So dx is a very small differential element along the x-axis. So the rate of change along the x-axis multiplied by L bar. So the difference in the concentration for a distance of L bar. So this is just like, or it can be written in a way like dN by dx into L bar, assuming delta x is very small under the limit of del x tending to 0, something like that. Okay. So replacing this expression N1 minus N2 here in this and using this derivative terminology, we reach to this expression. This is very simple. You can just plug in the mathematics and you can do that. So if you just replace N1 minus N2 with equal to delta n by del x into L bar. So L bar is there, which becomes L bar square divided by 2t bar and multiplied by dnx by x. Now minus sign is there, sorry, minus sign has to be there because which shows the electrons or holes, whatever, they are moving in the decreasing direction. The concentration is decreasing. So that's why minus sign is there. Now, so what this flux equation becomes finally is minus L bar square divided by 2t bar derivative of nx by x. So in this expression, this term minus, L bar square divided by 2t bar, this term is known as the electron diffusion coefficient. Same will apply to the hole. In that case, it will be known as the hole diffusion coefficient and represented by d subscript p, d subscript n. So the unit of this, which is evident from here, L bar square, which is centimeter or meter square, so distance square divided by time. So here normally it is represented in terms of centimeter square per second. So now we are fairly close to the current, diffusion current, because we know the flux now, flux of this charge carrier. So we just need to multiply it by the charge, and then we can get the diffusion current. So as I said, like we just need to multiply this with the charge carrier, the charge. So in case of electrons, we use minus q charge, and in case of hole, we just use plus q charge. So just multiplying this flux with the charge gives us diffusion current, which comes out to be q dn derivative of dx by ds. And similarly for holes, minus q dp dnx or dpx, if you just want to represent that gradient change with respect to holes, then it becomes dpx by dx. So interesting thing to notice here, in this diffusion current, there is no role of electric field. No value of electric field is required. It depends on charge, which is obvious, on the gradient, and it also depends on the diffusion coefficient. So diffusion coefficient is very, very important. As you can see, higher it is, higher would be the diffusion coefficient. So, and if you just want to learn more about that, so the expression for diffusion coefficient is L bar square divided by 2t bar. So L bar square by 2t bar. So under what circumstances it will be higher? When L bar would be higher and t bar would be small, right? So the mean free path should be large. If mean free path would be larger, then the diffusion current would be larger. Now we'll talk about the total current, As I said, like the current in semiconductor is because of these two major components. One is the drift and another is the diffusion. So we'll talk about both of them. So this is the total electron current, which comes out to be Q mu n, which is mobility, which we discussed in last lecture, concentration of the electrons, and electric field. This is electric field, plus diffusion current. So you can see there is no electric field. On the contrary, drift current depends on the electric field, also depends on the number of charge carriers. On the contrary, diffusion currents depend on the derivative of the charge carriers. Okay. And for holes, the expression remains same more or less, the minus sign will be there. So, and if we talk about total current, of course, semiconductor is about interplay between electron and holes. So, the total current would be equal to the current due to electrons and current due to holes. Now, from these expressions, it seems like, is it possible, like if drift and diffusion currents are equal and in the opposite direction, so maybe the current is effectively 0, but drift and diffusion currents are there or something like that. So we will investigate more about these equations, and we'll see what are the conditions which can be achieved in the semiconductor based on this drift and the diffusion current. Okay. So before we do that, let's talk about the movement of these charge carriers and the currents, just to develop some understanding. So for an example, let's say an electric field is being applied in this direction, Ex, okay, and the concentration gradient is like this, Nx divided by, oh sorry, not divided by, rho x, okay. So this shows the profile of the electrons and this shows the profile of the holes. Now what will happen, and what are the different flux that exist here and the different current because of those flux or these movements. So first let's talk about the holes. So as I can see here, the holes concentration is going down in this direction. So flux because of hole, I mean the diffusion flux, will be in this direction because concentration is higher here and lower here. So concentration is decreasing in this direction. So holes will move because of the diffusion. So current will be in the same direction. So I can say current density because of the holes and because of the diffusion of holes will be in this direction. Now similarly, if I talk about the drift current because of the holes will also be in the same direction, because holes are having the positive charge and electric field is in this direction. So because of the electric field, holes will move in this direction. So flux of the, because of the drift of hole will be in the same direction. So similarly, current will also be in the same direction. So you can say if the electric field direction and the concentration gradient direction is same, decrease in the concentration gradient, and electric field is in the, then both are the same direction. The current, diffusion current and the drift current will be in the same direction for holes. So this applies to the holes, for holes. Now we will talk about electrons. What happens in case of electrons? So similarly, you can see the profile of electron concentration. It is decreasing. So electron will again diffuse in the same direction. So I can say electron will diffuse in the same direction. Okay, and because electric field is in this direction, so electron will drift in this direction, the other way around. Okay, so if I just talk about the drift one, so it will be in the other direction, sorry, because the hole in the drift. If I say this is positive direction, then I have to use minus sign, or I can represent it as in this direction. Right. So similarly, diffusion current because of the hole will be in other direction, because of the negative charge. And drift current will be in this direction. Because electrons are drifting in this direction, so drift current will be in this direction. Electrons are diffusing in this direction, so diffusion current will be in this direction because of the negative charge. On the contrary, in holes, holes are drifting in this direction, so drift current will be here. Holes are diffusing in this direction, so hole current is in this direction. So while you calculate this, you need to keep this negative charge of electron into mind. Okay, so now we go ahead and we talk about more about the balance, and one more important thing is there, that from these expressions, the diffusion current can be fairly large as it depends just on the gradient. Even if the real charge carriers are small in number, gradient can be much larger. So even the minority charge carriers can build a huge diffusion current. On the contrary, drift current will remain small until and unless there is a large number of charge carriers are there. So minority charge carriers play a very important role in semiconductor devices because of the diffusion current, and diffusion currents plays a very, very important role, you can say, in semiconductor devices. So when we'll talk about PN junction, when we'll talk about JFETs, we'll see and BJTs especially, BJTs, we will talk about the role of this diffusion current, how these in PNP transistor and NPN transistors, so diffusion take place and which constitute a large amount of current. So these minority currents can be equally large of as of the majority charge carrier because of this. So the nature is different that you need to keep in mind. Now we'll talk about because of the drift and diffusion of these charge carriers, which leads to the built-in fields, okay, the fields in the semiconductor itself and how they act. So before we do that, we'll develop some basic equations. So we all know that the electric field is related to the electrostatic potential by this relation from basic electrostatics, very basic equation. Now this is, let's say, electric field, and this is potential. And we know that if I talk about electron energy basically, so electron energy is equal to minus Q potential with respect to X. So this is the electron energy, amount of work done in moving a Q charge in electrostatic potential against the field, and minus sign has been used because we are talking about electron energy. So for example, electric field is in this direction. So electrons would like to move on its own in this direction, but if we move electron by here from one position to another position, the amount of work done during that. So that is the energy gained basically, potential energy gain. So that's the electron energy. And if I just correlate this electric field and the electron energy, I can do so. Let's say this is my equation 1 and this is my equation 2. So I replace Vx here by Ex in this expression, and what I get here is electric field Ex is equal to, because if I just replace it with minus d by dx, and it comes out to be minus 1 by q Ex. Okay, so this minus will settle down and 1 by q can come out, it becomes 1 by q derivative of this electron energy. So this gives us a very interesting expression, Ex is equal to 1 by q derivative of Ex del x. Okay, so this is electric field, and this is electron energy, Okay. So, what we can conclude out of this expression? So, for an example, if we see, let's just talk in terms of maths. So, this expression will be positive, this derivative will be positive if Ex is positive, okay. And if let's assume x is in the for the both and whatever direction you choose to be positive direction. So, if electric field is increasing in this direction, let's say this is electron energy with respect to x, and if it is increasing in this direction with respect to x, derivative would be positive. So, electric field will be there in this direction with some magnitude, assuming the rate of change is constant. So, electric field will be in this direction. Assuming it is linearly changing, it will be some magnitude with a positive value. So, electric field is in this direction. If it is decreasing, if it would have been decreasing, maybe I would like to use, sorry, I do not have enough space. So, if it is decreasing in other direction like this way, if it is decreasing, then the magnitude would be minus, slope would be minus for this Ex with respect to x. So, electric field will be in this direction. Okay. So, from this expression we can calculate or check like what would be the direction of the electron energy, in which direction they will increase. Like here you can calculate, can say basically in the direction of applied electric field, electron energy will increase. So, if you have a piece of semiconductor and you applied an electric field in this direction, so electron energy will increase. So, this way you can draw the energy band diagram. Okay. So, let me draw some of them. This is just, I have already written that. So, what happens basically? In a semiconductor, we have drawn these energy band diagrams. We discussed that in lecture 2 in detail. Let us say this is conduction band and this is valence band. This is the condition when there is no electric field is there. Okay. You can say equilibrium is being maintained. Now, what will happen if I apply an electric field in this direction? Along the x direction, let us say this is x direction. So, what will happen? So, from this expression we learned that in the applied direction of the electric field, electron energy will increase because amount of work has to be done. So, how are we going to represent these band diagrams? So, this will be band. Electron energy E, and this is my applied electric field. So, just do not get confused that this is capital E, this is applied electric field, and again this is capital E. Okay. So, you can see they are band, no longer straight as they are here when electric field is not present, because electrons need to do the work, right, moving along the direction of the electric field, because their natural tendency is to go against that, right. So, if one electron is here and one electron is here, so here electron has more energy than here. So, this is very important. The reason to discuss is that when we apply electric field in the semiconductors, we should know what is the direction and how one can draw the band gap diagrams, etc. So, you can say in nutshell, the electron energies of conduction, valence and intrinsic bands will vary with position in presence of electric field, and how that will vary, it will be decided by this basic expression. Okay. So, let us go ahead then. So, let me just draw it when we have applied potential, okay, by battery. Let us consider a case of a semiconductor and it is in thermal equilibrium. So V is equal to 0 or whatever battery is there. So let's say this is of N type semiconductor. So what will happen? Let's say this is EI, okay, and this is your Fermi energy level. Since it is an N type semiconductor, so Fermi energy level is close to the valence band. This is EC, this is EV, okay, and this is, let's say, X, this is energy. More precisely, electron energy. Now, let's say for this semiconductor, we apply some potential. Everything is same, just that material is same N-type material, same dimension, same concentration of everything is same. So we just apply here of battery V. So because of that, electric field is there in this direction. Right. Now what will happen, since as I just discussed, electron energy will increase in the direction of the applied electric field. So diagram, what will happen to these band gap diagrams? So this is Ex, E, energy of electron. So they will bend like this. EI and EF, something like that. Okay. And how much will be this band? That's another interesting question. How much will be that? If I want to calculate, like, see, it would depend on the applied potential, right? So this difference would be equal to Q into V. Amount of work done, basically, this has to align this one, this has to align this one. So basically, you can say that if one has to move a charge from here to here, Q charge, against this potential of V, amount of work done is QV. The energy will increase by this amount, QV. So that's why you see it is increased in this direction. So this is, you can say, under biased condition, some biasing is there, and this is equilibrium condition. But if you remember, in the last lecture we talked about the invariance of the Fermi energy level, but Fermi energy level is not very invariant here. It's varying with the direction of X because equilibrium is not being maintained here. Biasing is there. If equilibrium would have been there, the Fermi energy level would remain same. Fermi energy level will not change. Others, these bands can band, right? Conduction band can band, valence band can band, even in thermal equilibrium because of this diffusion gradient and all that we'll talk about. But Fermi energy level will remain same. So there is a difference. But here all are bent because bias is there, external bias is there. I hope you understand this one. So now we'll talk about equilibrium that can be achieved because of these different currents. Okay, so what happens basically at equilibrium? No current flows in the semiconductor, and you can say a simple fluctuation which will begin, a diffusion current will settle down. It will set up an electric field which will redistribute the charge carriers by drift and diffusion current will become equal. So this will happen when there is no external electric field is there. So let's take the case of holes, and we derived in the beginning of this lecture this expression. So this part is my drift current, and this part is my diffusion current. Right. So if we equate it to 0, assuming equilibrium is there, no external field is there. Also there is no illumination. If there is an external illumination, it can create electrons and hole pairs, etc. So there is no change in the environment, no temperature fluctuations, no heavy temperature fluctuations. It's at room temperature. So in that case, there should be no current, right? So we can equate it equal to the 0. One can say, like, if there is a concentration gradient naturally initially, there can be a current, but ultimately that would be against the law of conservation of energy. But so ultimately current has to be 0, and let's see how it becomes 0. So if it is 0, then Ex is equal to, if we just put this equation equal to 0 and take this term, take one term on the other side and just derive the expression in terms of electric field, we get this term. Okay. So electric field is equal to d subscript p, diffusion coefficient, divided by the mobility mu subscript p divided by the concentration of the holes and the rate of change of the holes, concentration gradient profile. So now we need to come up with the expression of these px holes. If we have that expression, we can plug in into that and we can take a derivative of that expression, and then we see what happens basically. If you remember the lecture 2, we had this expression, lecture 2 and 3. So where the number of holes is equal to Ni, intrinsic charge carrier concentration, e raised to power Ei minus Ef divided by Kt. So what we are going to do now, we are going to take a derivative of this, and assuming Ei and Ex are the function of x, not just the constant. We'll talk about it, which one can be constant and which one. Initially, let's say they are function of x. So what comes out to be, if we just write down this expression as, of course, Ni has to be constant, but we need to keep in mind that we are discussing the case of thermal equilibrium, as I said in the beginning, thermal equilibrium. And we already discussed in last lecture that the Fermi energy level is invariant in thermal equilibrium. Yes, it varies, but here we have a potential. The one case we discussed just now has a potential, and the case we are discussing now don't have any potential, thermal equilibrium. So this cannot be function of x. Now we have to take a derivative of this. So let's take a derivative of this. Derivative of px divided by x. It comes out to be Ni e raised to power this expression Ei x minus Ef by Kt, and the derivative of this comes out 1 by Kt. Derivative of Eix divided by dx minus derivative of Ef Ex by x. So this is the expression here, whatever here it is. And since it is being multiplied by 1 by rho x as well, so this will settle down with that. 1 by Kt will remain, otherwise it will be cancelled out by this term. So the expression is this for the electric field. And as I said, thermal equilibrium Fermi energy level doesn't vary with x, so this will become 0. But yes, in thermal equilibrium case, these intrinsic energy level can vary. Conduction energy level can vary, valence energy band can vary. So this expression for electric field comes out to be And don't get confused, this electric field is not the external electric field, because I have been talking about thermal equilibrium. So this is the electric field which is the internal electric field. Which gets created because of the distribution of the charges. We'll talk about that in detail. So this is the internal electric field under equilibrium condition. There is no external electric field, no temperature change, no illumination, no any other factor which can change the equilibrium. Okay. So now let's see. So, we have got this expression we just derived. We also got this expression which decides how these in the presence of electric field these bands will vary. If you remember, we talked about that in the detail. So, this is our equation 1, this is our equation 2. Okay. Now, we can equate these two equations. What we will get? dP by mu p divided by 1 by kT dEI by dx, which is equal to 1 by q derivative of dx. These derivatives terms will be equal, so this will cancel out, so we get this expression. This is known as the Einstein relation basically. So, this allows to calculate, if you know d, you can calculate mu, if you know mu, you can calculate d. So, diffusion coefficient and mobility is equal to kT by q. K is the Boltzmann constant, T is the temperature, Q is the charge. So, if you remember in the beginning of the lecture I said diffusion and mobility has to be related. Though their origins are different, diffusion happens because of the change in a difference in the concentration, and mu happens because of the electric field, but they are related because ultimately motion is restricted by scattering. So, from here this is a wonderful expression and it is very helpful. So, d by u kT by q, you can use that. If 1 is given, d is given, then you can calculate mu, and mu is given, you can calculate the d. And this also shows the relation between both of these expressions. Okay. So, now we will talk about like from where this electric field came, right? When there is no electric field is applied, so from where this internal electric field came. So, let us discuss a case. One more thing, like d by mu is equal to 0.026 volt at room temperature 300 Kelvin. So, which comes out to be around 26 millivolt, approximately 0.0259, something like that. So, before I explain the creation of this electric field and all that, let us talk about some diffusion coefficient and the mobility of some different semiconductors. Okay. So, let us talk about three most popular ones which we will discuss thoroughly in this course: germanium, silicon and gallium arsenide. So, their values, diffusion coefficient values, mu n values, diffusion coefficient of holes, mobility of the holes. So, we will talk about these 4 parameters, and the unit of the diffusion coefficient is centimeter square per time, and similarly for mobility it is centimeter square volt per second. Okay. For germanium it is, let us say 100, 35, 220, and if we talk about the mobility, which we already know, it is 3900, 1350 and 8500. So, you can see that for gallium arsenide it is not just the mobility which is higher, it is also the diffusion coefficient which is much higher than silicon. So, you can say like it is close to 6 times, more than 6 times basically. So, that makes a lot of difference. That is why these gallium arsenide are used in this fast electronics. So, diffusion coefficient is higher, mobility is higher. Okay. And similarly for germanium, you can say both are higher than silicon. On the contrary, for holes, that is not the case. So, it is same like as of mobility. So, the values are 50, 12.5, 10, and if we can recall that this is what we discussed, something like that. So, here the germanium is better. Germanium is better than gallium arsenide and of course silicon. Okay. But most of the guys are n-type based, so gallium arsenide wins, and that is why gallium arsenide is very important. Now, we will talk about more like how this band formation take place. but let me just discuss the relation of this diffusion coefficient with the temperature. So if you remember when we talked about the mobility in the last lecture, it was very evident that we discussed in very detail like how does it depend on the temperature. There were two major scattering mechanisms that we discussed because of the impurity, because of the lattice atoms, and it varies something like T mu, if you remember in the last lecture. Also we talked about that how this diffusion varies as a function of concentration gradient. Okay, so it was like that. So higher is the concentration of these impurities, acceptor ions or donor ions, they will affect the basically you can say impurity scattering. They will make it more dominating because more impurities are there, more chances that these charge carriers will get will be scattered or will be interacting with that. So this was lattice scattering. Okay. So if I talk about diffusion, of course diffusion do depend similarly on the impurity concentration. So it do decreases with the time in the with the increase in the concentration of these impurity ions. So diffusion do get decreased this way. Okay. So for either it is silicon or gallium arsenide, either it is for electrons and holes. So for holes, sorry, for electrons and so as for holes as well. So similar relations has been obtained. Okay, so this is something that one should know, that how it will behave or change when the concentration gradient is there. Now I will talk about the internal electric field. As I said, like from where this electric field is coming. So let's talk about that in detail. So let me just I just need to have one slide. Okay, so let's discuss a case of PN junction. Actually, we will be talking about PN junction in later lectures in detail. So, but let's talk about that just to understand from where this electric field is coming, from this balance of this diffusion and the drift current. So, let's say this is my two semiconductors P and N. Why I am taking the case of a PN junction? Because I want to take an extreme case where there is a concentration gradient is there. So, this type of this part of the semiconductor, let's say this is metallurgical junction. So, this part of the semiconductor P type is doped with the impurities which are basically acceptor. Okay. So, this is a hole rich region. So, the impurities will carry a negative charge because they are accepting the electron, right, from the host. Now, there are free holes because it's a P type. So, you can say holes are there. And similarly, this is N type. So, donor atoms will have a positive charge because they are donating the free electron. So, electron are here, free electrons are here. So, this is, let's say, just before the both PN junction are being diffused together. P type and N type is being diffused together. Okay, just before. So, you can say it's a hole rich region and this is electron rich region. And there is a concentration gradient is there. So, hole would like to move from here to here, from P to N side, and electron would like to move from N to P side. So, this is P to N, this is N to P, and this is, you can say, electron, and these are holes. So, largely these are this movement is because of the diffusion, right. And again, there is a thermal equilibrium. No electric field is being applied. No electric field, no external electric field is there, and no temperature change. Temperature changes there with time, and also there is no illumination, etc. So what will happen as soon as these electrons will move from here to here, and these holes will move from here to here, they will recombine. They will recombine, and this region will be depleted of these charge carriers. And because of these charges on these ions, negative charge on the acceptor ions and the positive charge on the donor ions, so there will be an electric field. Let me just draw a more magnified image of this. This is the metallurgical junction, x is equal to 0. So let's say this is charges because of the acceptor and the donor ions. So you can see there was a balance, right? But now these holes are depleted and these electrons are depleted because of the recombination. So holes are there. Despite there is a concentration gradient, now there will be no movement. Okay, so in this region, because now there will be an electric field, charge is there from positive to negative, there is electric field E, right? Because of this is internal electric field, there is no external electric field, and this will further restrain the movement of these electrons in this direction and holes in this direction. As you can see, the direction of the electric field is in this direction, and concentration gradient is in this direction for the holes, and for electron is in this direction. So this electric field would have allowed the movement of holes in this direction or electron in this direction. But unfortunately, the circumstances are like that. Holes are here and electrons are here. So this will not further allow any diffusion of the electrons and holes. Moreover, you can ask, how about the binarity charge carriers? Despite this is a p-type semiconductor or n-type semiconductor, there would be some minority charge carriers. Of course, they can move, but overall effective current will be 0. And this is how it leads to the formation of the electric field. Of course, we will talk more about this p-n junction diode in the next lecture. And let me give you one more example. So for example, what happens, let's say if you have a conductor with the p-type semiconductor, or n-type semiconductors full of electrons, not the case of p-n junction which we are discussing right now, which we were just discussing. So what will happen in that case? If there are lots of electrons, just electrons, how this diffusion current will be there, and it will lead to formation of an electric field. So what happens? Again, positive charge ions are there, right? And they have free electrons. These are donors in this region, and then let's say the electron starts moving here. So once the electron starts moving here from region of high concentration to low concentration, these donors will try to pull them back, right? They will try to pull them back because of the Coulomb interaction. So electric field is in this direction. Again, positive charge, negative charge, electric field is in this direction. Electron also wants to move in this direction because of the concentration gradient, but this electric field not further allow their movement, and an equilibrium will be achieved at some stage. Okay, so this is how the electric field, internal electric field leads, formation of the electric field leads in the semiconductors. Because of this diffusion current, these carriers move from one place to another place. We'll talk more about that in very detail when we talk about these p-n junction diodes, and this distribution plays a very important role. So now I will come to the last topic very quickly, the Poisson's equation. This is named after French mathematician Simon Poisson. The pronunciation of the Poisson can be different in French and English. So what it says basically, so it says that the double derivative of the potential is related to the charge. So why I am talking about that, why it is so important. So as I said like this, distribution of charge can take place because of the diffusion of the electrons and holes. So how you would like to calculate the electric field? For example, just in the last slide, if I am interested in calculating the magnitude of this electric field, how can I do that? So I can do that using these Paulsen's equations basically. If I know the total charge in that region, then I can very easily calculate. So one of the very quick derivation of this is from the Gauss law, one of the Maxwell's equations. Okay, so you can say D is equal to epsilon E. If you just replace it here, it becomes del dot E is equal to rho by epsilon. Rho is your charge density, and we all know this relation which we just used, very basic electrostatic, and if we just replace this one, then we can get this Paulsen's equation. In fact, we don't need to use this Paulsen's equations, we can just from this expression itself we can calculate. For an example, if you just want to calculate the electric field, so derivative of electric field is equal to Q by epsilon P minus N plus Nd plus Na. So these are total charge. In case if it is just an N-type semiconductors, you can ignore other charges. So this way we can calculate the electric field profile once we have the charge distribution. So if I just summarize, today we talked about the diffusion of the charge carriers, why diffusion happens, because of the concentration gradient, on what parameters it depends, the role of the diffusion coefficient, and the total current, combination of the drift current and the diffusion current, and what will happen when there is a thermal equilibrium is there, right? Drift and diffusion current will be 0, there will be an electric field, internal electric field will generate, and in such circumstances you can say the electron energy of the conduction band and the valence band will vary with respect to x, even intrinsic energy will vary, okay, but Fermi energy level will remain same because there is no external field or thermal equilibrium or equilibrium is maintained. And if equilibrium is being not maintained, like by applying an external battery, Fermi energy level will also change with x. And how to calculate this electric field using the Paulsen's equation. If you know the charge distribution, we can very easily calculate the electric field. In future lectures, we will do that. So I think we are done for the today. Thank you very much.